Hello, this is Physics 104A at Porterville College, Chapter 8 homework, starting with number 11, with the space explorers landing on a planet that has the same mass as Earth. The strength of gravity on this new planet is 19.6 newtons per kilogram because it's 2 times 9.8. We know that strength of gravity, or acceleration due to gravity, is going to be g times the mass of the planet divided by radius. So here I have g sub nu, which we already know is 19.6, is equal to g, the gravitational constant, times the mass of the Earth, because our new planet is the same mass, divided by radius of the new planet squared. And so we're going to use this equation and solve it for radius sub nu. Here's the algebra that I go through. It's equal to square root of g times mass of Earth divided by g sub nu. Plug in those numbers, and we get 4.51 times 10 to the 7th meters. By the way, that comes out to be the radius of the Earth divided by the square root of 2. Another way to solve that problem is to say the force, we start with Newton's equation. The force is g, mass of Earth, times the mass of any particular object divided by radius sub nu squared. The force of gravity is 2 times mg, 2 times the weight on the Earth. And you can see that the mass of any particular object is going to cancel out. And once again, we're left with what we had in my first solution. R sub nu is square root of g times mass of the Earth divided by 2g. Number 15. Two identical lead spheres, centers 14 centimeters apart. Find their mass. We're going to use Newton's equation for gravity. Since they are identical, they have the same mass, so instead of saying m1, m2, let's just say m squared. You're going to take this equation and solve it for mass. So mass equals square root of force times radius squared divided by g, the universal constant. Force is given in micronewtons, so remember to make that times 10 to the negative 6. And you should get 8.57 kilograms, or I'll round up to 8.6. Number 17. Okay, the top of the Sears Tower, where it's reading, is 1.36 millimeters per second squared lower than at street level. Find the building's height. Here's my diagram of the tower. There's at the bottom of the tower, it's at the radius of the Earth. The top of the tower is radius of Earth plus height, and it's that height we're going to solve for. There's our difference in g. So we can start by saying the acceleration on the ground minus the acceleration at the top, that's going to give a positive number, is equal to the difference in g. And let's solve for what the acceleration is. That's going to be big G, mass of the Earth, divided by, at the ground, that's radius of Earth squared, minus, for the top of the tower, big G times m divided by radius of the Earth plus height squared, equals difference in g. From here, it's just a matter of algebra. We want to ultimately solve for h, and that'll take us a few steps. Let's do it. Here, what have I done? I've divided by gm, divide the entire equation by gm, and keep in mind, my whole point here is just to isolate h. I have gotten all the non-h terms over to one side of the equation, so 1 over re plus h squared equals the rest. Pay attention to your plus signs and minus signs. And actually what I've done here, going between this line and this line, I've multiplied both sides by -1 to make this left-hand side positive. Then from this line to this line, I take the reciprocal of both sides. It's much easier rather than trying to go through arithmetic of finding a greatest common denominator between these fractions. Just take it and put it all to the -1 power. Calculators are nice and convenient for doing that. And finally, we're going to take the square root. Radius of the Earth plus height equals all that and the square root of it. So once you do what's on the right-hand side of the equation, you just subtract radius of the Earth, and the height is, no, that whole square root term comes out to be 6,370,441 meters. Then we subtract away the radius of the Earth, 6,370,000 meters, and we get 441 meters as the height of the tower. Number 18. At what altitude will a satellite complete a circular orbit in 2 hours? Well, in class we figured out the circular orbit for the International Space Station. We found that to be about an hour and a half. I think it was 92 minutes. And so we expect it's going to be a bit higher because it's a longer period than the International Space Station. Let's use this equation. It's in the book, equation 8.4. Period squared equals 4 pi squared radius cubed over gm. I have here on the side the various constants you'll need to plug in. You can look those up in the front flap of the book. Algebraically, we're going to solve that equation. R equals, that's a cube root sign right there. Cube root of gmt squared over 4 pi squared. When you plug those in, you get a radius of 8.056 times 10 to the 7 meters. Now that is the radius of the circular orbit. The question asks what altitude. Altitude means height above the Earth's surface. So we're going to take our value for radius, subtract the radius of the Earth, and get 1,690 kilometers. Number 21 is similar to the last one. Calculate the orbital period for Jupiter's moon Io, which orbits, and there's a given distance from the planet's center. Alright, so this one we will just straightforward use the period equation. Period is, well, we solve it for period, square root of 4 pi squared, r cubed over gm. We need the appropriate numbers. You can look these up in the table of astrophysical data, Google search it, whatever you choose, but the mass of Jupiter is 1.9 times 10 to the 27 kilograms. We need to remember to use for radius, don't use the kilometers that are given in the book, but rather we need that in meters. And you should get 1.53 times 10 to the 5th seconds, which is 42.5 hours, which is 1.77 days. Number 25. 25, a suborbital mission goes into space for a brief period. It's a simple up and down vertical path. Because it's an up and down vertical path, we know that when it gets to the top, it's going to have kinetic energy of 0. That's a turning point. How much energy does it take to launch the instrument on a vertical trajectory that peaks at 1,800 kilometers altitude? Alright, here's my diagram. There's the Earth. We can call the launch position 1 at the surface of the Earth, and position 2 to be the peak. It's going to just launch straight up, get to the top, and turn around. Conservation of energy. We'll start with energy 1 equals energy 2. Now the energy at 1 is kinetic energy, and that's what we're solving for. We don't want to break this down into 1/2 mv squared because the problem is not asking us for velocity. So it's asking us for kinetic energy. We'll keep it like that. Kinetic energy 1 plus potential energy. Remember, potential energy, based on how we've defined it, with as being 0 at infinite distance, it's going to be negative. So negative g, mass of the Earth, mass of the instrument divided by radius of the Earth, plus energy 2. This is all going to be potential energy, no kinetic energy. Negative g, big M, little m, over, and here's its new distance, radius of the Earth plus height. Go through the algebra, solve for kinetic energy, and here's what it comes out to be. GMM plus the difference of those two reciprocals, and I get 3.17 gigajoules. Right here on the side are all the various constants you'll need to plug in. By the way, if we neglect changes in little g, and the frowny face there says this is not a good way to go about doing physics, but if we neglect the changes in g, we set up energy 1 equals energy 2, kinetic plus potential equals potential, and what we would then get, and this is the way we might have done such a problem before we learned about gravitational potential energy, we would say kinetic energy plus potential of 0 equals simply mgh. And that would have given us 4.06 gigajoules. Now, that's not the right answer. The right answer is 3.17 gigajoules. It doesn't take as much as prior to this chapter we would have thought it would take, because gravity diminishes as you get farther away from the Earth's surface. Number 27. A similar diagram, similar problem. What vertical launch speed is necessary to get a rocket to an altitude of 1,100 kilometers? This is just like the last problem, except now we're solving not just for kinetic energy, but for speed. I have a similar diagram here. You notice now, as opposed to number 25, I've broken down kinetic energy 1 as 1/2 mv squared. Everything else is the same in the equations. Little m, the mass of the whatever we're sending up, the spacecraft, is a term, it's a factor in every one of those terms, so we can divide it out. We're left with 1/2 v squared equals gm times the difference of those reciprocals. Solving for v, it's a square root at the top of your screen. Square root of 2gm times the difference of the reciprocals of the radii. And in the next line with the red asterisk, I ran out of space while plugging in the numbers in. So here we go. 2 times, this is g, this is the mass, and this right here I've expanded on this line just to show you the numbers that I plug in. And we are adding a height in this term of 1,100 times 10 to the 3rd meters. And for the final answer, we get v equals 4.29 kilometers per second. Number 36. A water tower over you. How much does it decrease your weight? Specifically, it asks by what fraction is your weight reduced due to the water's gravitational attraction. Here's a diagram. I have a distance of 15 meters between, let's just have it as the center, okay, 15 meters directly below the center of a spherical water tank. So 15 meters between its center and your center. Well, the force of gravity from the tank, you can use Newton's equation, plug those numbers in, and you get force sub T, force of the tank, 1.186 times 10 to the negative 6 times whatever your mass is, and that's the number of newtons. But the question is asking, by what fraction is your weight reduced? And at some point, we expect that mass is going to cancel out. So let's do this. we can say weight reduction divided by your old weight. That'll be the fraction that it's reduced. So weight reduction is the force of the tank. It is pulling you up, so it's reducing your perceived weight, divided by your old weight, your weight that the Earth is pulling on you. And that becomes the 1.186 times 10 to the negative 6 times mass, divided by your weight, just from the Earth, is mg. The masses cancel out, and we get 1 times 10 to the negative 7. That is unitless. Yes, that is unitless because it's just a fraction. I've taken it just to one significant figure because the mass of the water tank is given to one significant figure. Number 44 always helps to draw a picture. In problems like these, satellites A and B are in circular orbits with A twice as far from Earth's center as B. How do their orbital periods compare? Here I've drawn satellite A, satellite B. Earth is red for some reason. Just go with it. We're going to use this equation. T squared equals 4 pi squared r cubed over gm. How do their orbits compare? Let's set that up as a ratio. Since the equation is given in terms of t squared, let's set it up as t squared ratios. So t of a squared divided by t of b squared. And here is t of a. Notice that it's using radius of a, divided by t of b squared. And so I'm multiplying by its reciprocal. All these terms go away. The 4 pi squareds, the g, the mass of the Earth. And so what we're left with is that ta squared over tb squared is ra cubed over rb cubed. Let's solve now for the periods. So we'll take the square root of both sides of the equation. Period of A divided by period of B equals the square root of RA over RB cubed. Now I'm going to do a substitution that RA is twice RB, so there it is. Now the radius of B cancels out, and we're left with 2 cubed. And so that's going to be 8. We're taking the square root of it. So in the end, we have that the ratio of the two periods is 2 square root of 2, which is about 2.83. So we can write it this way, that the period of A is 2 square root of 2 times the period of satellite B. Number 59. This problem, at first glance, seems like it might be like number 25 and number 27. And it is, sort of, except there's one little change. It says a missile's trajectory takes it to a maximum altitude of 1,200 kilometers. If its launch speed is 6.1 kilometers per second, how fast is it moving at the peak of its trajectory? An interesting question. How fast is it moving? In problems number 25 and number 27, we were dealing with a vertical rocket that went straight up, and at its peak, it had a speed of 0. But now we're being asked how fast is it moving at its peak? Why would it have any speed at its peak? Because it's not vertical. You look at this diagram here, it's being launched at 1, but now I've got it in this orbit right here. So at 2, because it's not a one-dimensional problem, at position 2, it still has velocity. So we're going to set it up as energy 1 equals energy 2. It's conservation of energy, just like problem numbers 25 and 27 were. However, we need to recognize that it has kinetic energy at position 2. Not only do we have to recognize that, but in fact that's part of what we're solving for. We're solving for that speed. So 1/2 mv naught squared, and sorry about the subscript. Since this is energy 1, I probably should have called that velocity 1, but that's the kinetic energy at launch, plus negative gmm over radius of the Earth, that's potential energy, equals, when it gets to that peak, 1/2 mv squared, there's the v we're solving for, plus negative gmm over radius of the Earth plus height. We go through the algebra. One thing we see is that the mass of the rocket divides out because it's a factor in every single term. Go through the algebra and you should get this right here. That velocity is the square root of two main terms. The first term is the original velocity, v0 squared. But then there's another term. There's a reduction in velocity due to the potential energy changing. And that part is 2gm times the difference of those two reciprocals. So that is the equation you should get. Once you get it, plug in those values that are on the left-hand side. V0 is 6,100 meters per second. We have a height of 1,200 times 10 to the third meters. All the others are the usual constants, and we should get a speed of 4.17 kilometers per second. The last problem. Number 61. An elliptical orbit around the Sun. Mercury's orbit varies. So here we have position 1, which is perihelion, its closest point to the Sun. Here we have position 2, aphelion, its farthest point from the Sun. Here's the given information. V1 is 59 kilometers per second. V2 is 38.8 kilometers per second. We have R2, and we need to find R1. We need to find the position at perihelion. And we set up conservation of energy. E1 equals E2. Again, where I've made 1 according to the picture that I showed, perihelion, and E2 is aphelion. Kinetic energy plus potential, the same setup as in the last problem, equals kinetic energy plus potential. The m's divide out, so the mass of Mercury doesn't matter. It doesn't matter even if it were a small artificial satellite that we put in that same orbit, the mass doesn't matter. We are solving for R1, so I'll take you through the algebra that I did to solve for R1. You might find a slightly different technique. I first subtracted this 1/2 v1 squared to get it to the other side, and I've multiplied both sides by 2 just to get rid of those fractions. Then over here, it's possible that I, in afterthought, regretted multiplying by 2 because here now I'm dividing both sides by 2. Actually, I'm dividing both sides by negative 2gm. And my reason for doing that is just to, it seems the quickest way for me to isolate r sub 1. And so I have negative v2 squared over 2gm plus v1 squared over 2gm plus 1 over r2. Now, since that is the expression for 1 over r1, just compute with the calculator what that right-hand term is and take its reciprocal. Put it to the negative 1 power, and you've got r1. By the way, you're going to need, for the computation, the mass of the Sun, 1.99 times 10 to the 30th kilograms. And what we get is the R1, the distance from the Sun to Mercury at perihelion, is 4.60 times 10 to the 10th meters. And that's the end of the Chapter 8 homework.